Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors and the Geometry of Space, Section 4, the Cross Product, Video 2, Example of Calculating a Cross Product. We are going to calculate just one example because from a numerical perspective, the actual values don't matter. It's the process, and I think one example should suffice. We will calculate more cross products, don't get me wrong, but the focal point of this video is just to demonstrate how to calculate it. So for our example, we're going to calculate the cross product of the vector 1, 3, 4 and the vector 2, 7, -5. Then we're going to verify that the cross product, the resulting vector, is orthogonal to both 1, 3, 4 and to 2, 7, -5. All right, so let's start with identifying stuff. Now, this may seem somewhat trivial, but when you're first learning to do cross products, the hardest part about it is keeping up with everything. So if we call the first vector u and the second one v, this would be u1, u2, and u3. So u1 equals 1, u2 equals 3, u3 equals 4. And the second vector would have v components. v1 is equal to 2, v2 is equal to 7, v3 is equal to -5. All right, in order to find the, make sure you guys are actually seeing this. Yes, okay. In order to find the cross product, I'm going to use the same gimmick as we did before. All right. The first position, well, each one of them starts with a U, but the subscript we write is the subscript for the next position. So since we're in the first component, we're going to start with U2. And then for the second component, we're going to go over and start with U3. And for the third component, we're going to go over and start with U1. Then we're going to attach V's to each one of them. And remember that in each component's position, we do not have a subscript that matches that position number. We have a different subscript. So we don't have any subscripts of 1s in the first component. So the first V over here is going to have a subscript of 3. In the second component, we have no subscripts of 2. So this V is going to have a subscript of 1. And in the third component, we have no subscripts of 3, which means this V is going to have a subscript of 2. Then from each product in the components, we're going to subtract what we would get if we switch the subscripts for each of the variables. So for example, in the first component here, instead of U2 V3, we're going to say U3 V2, comma. In the second component here, we're going to switch the order of the subscripts. So instead of U3 V1, it's going to be U1 V3. Being very careful to draw my V's pointy and my U's curvy. And on the third component, again, we're going to switch the subscripts. So it's going to be U1, it's going to be U1 V2 minus U2 V1. Okay. Now let's figure it out. Second U is 3 times the third V is -5 minus the third U is 4 times the second V, which is 7. Second component of the cross product, third U, which is 4, times the first V, which is 2, minus the first U, which is 1, times the third V, which is -5, comma. Last component, first U, which is 1, times second V, which is 7, minus second U, which is 3, times the first V, which is 2. Let's make sure we got that set up correctly. Second U is 3, third V is -5, third U is 4, second V is 7. I'm right here. I'm on the second component now. Third U is 4, first V is 2, minus first U is 1, third V is -5. And then lastly, first U second V minus second U, first V. I think everything is good. Let's see what this equals. We'll expedite the arithmetic. This is negative 15 minus 28. Negative 15 minus 28 is negative 43. And for the second expression, this one's easier. 4 times 2 is 8. 1 times negative 5 is negative 5. 8 minus negative 5 is 13. And for the third one, 1 times 7 is 7, minus 3 times 2 is 6. 7 minus 6 is 1. Okay, that was relatively harmless. For some reason, that's not sitting well. No, I'm looking. That's the answer I got. This is actually example 1 on page 559 of the book that we're currently using, but I didn't look at it. They did do it in IJK form, and in fact, they calculated it a little bit differently, which I'll demonstrate in the next video. So calculating the cross product by hand is tedious, but I want to check that it's actually the cross product. So we're going to show that it's orthogonal to both. Now, how do you show a vector is orthogonal to another? The dot product is 0. So we're going to take what we claim is the cross product, and we'll form the dot product with both of the original vectors in turn, first being 1, 3, 4. Remember how dot product works. It's the sum of the products of corresponding components. The first components in these vectors are negative 43 and 1. The second components are 13 and 3. And the third components are 1 and 4. Excuse me. So we get negative 43 plus 39 plus 4, and surprise, surprise, it did what we expected. It was 0, which means the vectors are orthogonal. But the cross product is supposed to be orthogonal to both of the original vectors, not just the first. The second original vector was 2, 7, negative 5. So we also have to check, and I'm at the very end of the page here, what happens if we found the dot product of what we claim is orthogonal with the dot product with that vector and one of the orthogonal vectors, 2, 7, negative 5. I'm going to go through this one a little bit more quickly. Negative 41 times 2 is negative 86. In the middle, 13 times 7 is 91. And at the end, 1 times negative 5 is negative 5. Yep, negative 86 and negative 5 is negative 91. So it does cancel to give 0. All right, in the next video, we're going to look at a couple of different ways to remember how to calculate the cross product.